and advising on schools infrastructure resilience in Philippines, Salvador, Dominican Republic, and Pakistan. She's a director of the International Association of Earthquake Engineering and a founding member of ICOMOS ISCARSA. She has recently been awarded a UNESCO chair in disaster risk reduction and resilience engineering. The title of her contribution will be Multi-Hazard Risk and Prioritization for Architectural Heritage Applications to the Philippines. Dr. Pere Roca will follow and is a professor of the Technical University of Catalonia, where he carries his activity as lecturer and researcher. His work focuses on non-destructive inspection techniques, structural monitoring, structural analysis, and strengthening technologies. He has published more than 200 papers in conference proceedings and journals. He is co-editor of the International Journal of Architectural Heritage. He has been consultant in over 100 case studies, including 5 UNESCO awards. The title of his contribution tonight is the ICOMOS ISCARSA Guidelines on the Analysis, Conservation, and Structural Restoration of Architectural Heritage. Dr. Vitor Carlotto will conclude this evening presentation, and is a geological engineer from the University of Cusco. Postgraduate and doctorate in art science at the University of Grenoble, France. From 1982 to 2004, he was professor and researcher at the University of Cusco. He has 40 years of experience in geological exploration, including geological research in archaeological sites. From 2004 to 2008, he is member of the Scientific Committee of the UNESCO International Geoscience Program, IGCP, and since 2014, he is a full member of the National Academy of Science of Peru. The title of his contribution will be Conservation Experiences in 3 Pre-Hispanic Sites in Peru, Machu Picchu, Choquequirao, and Karaal. Now, without further ado, I leave the floor to Professor Dina Dayala. Thanks.
Thank you very much, Valentina, for your very kind introduction. And thank you. I'm trying to share my screen now. I hope that you can see my slides. Yes. Can you please let me know whether you can see my slides?
We can see it and hear you fine. Thank you.
Thank you. Thank you very much. So without further delay, I will start my presentation, but I would like to, first of all, thanks the International Organization of the Engineering Organization and Dr. José Macharet for the invitation to this very interesting webinar, and to give me the possibility of sharing my work with so many interesting and well-versed colleagues. So what I will be talking about tonight is an approach to multi-hazard risk and the possibility to prioritize interventions for architectural heritage. And so that we can better understand what I'm talking about, I will focus on the Philippines, because we had some direct experience working with colleagues in the Philippines to look at their heritage. So so yes, this first map provides show of this is a map of the world. You can see that it's slightly deformed from what geographically we are used to see. and shows the basically the mapping is done by World Mapper and depend on the intensity in any given country of the particular indicators that we are mapping. So here we are mapping UNESCO World Heritage sites. We see that there is a great presence of them in Europe, less so in China or in the Americas. This has to do with, of course, where the UNESCO World Heritage movement started from. In Peru, indeed, there is a large number of UNESCO sites. And when we look at the Philippines, we see that more or less the geographic mapping is corresponding to the World Heritage Sites mapping, i.e. They don't have very few, but they are within the expected average of what they should have given the countries. So if indeed, however, we map the geophysical hazard damage, so earthquake, volcanoes, and landslides and so on, we can see now that the Philippines has fallen quite considerably because the level of hazards in the Philippines is very high. And similarly, if we look at the climatic hazard damage, they are indeed exposed to typhoons and to flooding and weather events quite often. So if we then summarize this multi-hazard profile, we can see that, and this is based on data produced by the Global Risk Data Platform of the UN, we can see that there is quite a large number of that both earthquake, wind, cyclone winds, and floods have a large incidence throughout all the islands, and that the return periods are quite high. And if we sum up all the hazards, and this is mapped here in red, we can see that the multi-hazard average annual loss runs in the thousands of USD million. So it's actually a very high proportion. It's one of the countries where the losses are the greatest. And we know very well that hazard losses and let's say disaster means that a country can never properly develop because it needs to rebuild and reconstruct and renew every time. So this is not clearly a sustainable situation. For the rest of the talk, I will concentrate on two islands, Bohol and Cebu. Bohol and Cebu were affected by an earthquake in 2013, a very damaging earthquake. And then a few months later, they were also affected by the Yolanda or Hainia typhoon. And this actually brought further destruction on the collapse and damage already caused by the earthquake. Just to give you an idea, I'm going to focus on this building here, which is the Loboc Cathedral. Here we have a river and a bridge that went nowhere, but this is another story. You can see from this aerial view that the church is divided in two and that the transept is completely missed. The Philippines, and in particular those islands, have heritage that goes back to the Spanish period, where several Catholic churches were built by the missionaries and the monks. Some of them are strikingly similar to the cathedrals that we see, for instance, in Peru, in Lima, and in other cities, in Inca, because they were built by using very much the same technology that was already distributed worldwide, and this is very interesting, in the 16th and 17th century through the orders, through the fathers' orders that, let's say, distributed, they disseminated the religion in this country, and at the same time, they also used local understanding and local technical construction to improve what they were doing. So this is the damage that was caused by the earthquake, and as I said, the complete destruction of the transept. And then there was flooding that was caused by the nearby river. And here we can see the level of damage of the flooding. The water reached more than 1.20 meters high, almost, in fact, in some parts 2 meters. And of course, then there was the issue of the water being absorbed into the structures. And then finally, also damage to the roof due to the Yolanda typhoon. This case is not an isolated case. In fact, there were at least other, we studied about 20 church complex where you had both the church, the convent, sometimes kitchen structures and other bell towers and so on, dormitories, schools, and other interesting and some private homes where this damage was recurring. So the National Historical Monument Commission required the systemic approach to this problem. And we were fortunate enough to work with them to develop such systemic approach. So when we're talking about multi-hazard risk assessment, this is usually due to the fact that we are aware of the fact that there are several hazards. We are aware that of the fact that there is a wealth of assets that are exposed to such hazards, and we need to identify, let's say, the resources needed. And then we need to compare the resources needed with the resources available. And very often the resources needed are much greater than the resources available. And therefore we need to think about who is in greater needs of being prepared for the next hazards. So which of these assets needs more restoration? And shall we target the hazards shall we target the assets that are where the hazard is greatest, or shall we target within a nation, or shall we target the hazards where the assets where the hazards are most recurring, or shall we target the assets that are more vulnerable? So in order to do this, we need, as I said, a systemic approach. We need to, first of all, have clear hazard profile for different hazards, for instance, seismic, flood, and wind. And in this sense, the Philippines national government has organized itself in such a way that there is a good understanding of what the hazards are at geographical level in each of the islands and what are their magnitude, with quite clear understanding of return periods and intensities. We then need to understand for each assets, what is the level of exposures? And this can be done by many ways, by research, by archival information, by on-site data collections, by satellite and general street map data, for instance. And then finally, we need to determine their vulnerability, both to earthquake loading, to flood loading, and to wind loading. And the understanding of this vulnerability have to be commensurable, have to be comparable, because if they are in different scale and in different quantity, we cannot then arrive at a real risk assessment that allow us to really prioritize and understand the different level of risk for the different level of hazards. So once we have a result here, then we can start planning the risk reduction measures and quantify them and look at the final bill and understanding what are the budgets and what are the requirements, and therefore then make recommendations. So this approach can be either empirical or analytical. It can either be based on observational side or can be done at with let's say mathematical model and numerical models. So depending on the level of information and the level of approach, we can have different level of risk assessment. So for instance, here in the green box, we are considering what we call a level 1, where we will do a rapid visual surveys. This will allow us to determine what we call risk prioritization, just say that certain building in a particular environment or in different environment, but exposed to the same hazards, might have different priority, and we will see how we can determine these priorities. Or we can have an extreme, very detailed modeling that looks at one particular asset. So for instance, we could study in very great detail the Loboc Cathedral that I've just presented, and we could do very advanced model, non-linear, with a high probabilistic model of the hazards if we have sufficient information at the site, and come up with this. Or we can choose intermediate level, so where we can indeed develop some simplified structural modeling, which allow us to have sufficient engineering input in the process by which we can understand how mechanically this building responds to the loading of and the effect of the hazards, and therefore allow us to make informed decision on the mitigation measures that we are considering in terms of repair, restoration, or strengthening. And at the same time, we can be generic enough that we can treat several buildings so that we can come to build up what we call fragility or vulnerability functions, which then allow the, let's say, stakeholders, the organization that look after this building to understand and make a decision in relation to actual numerical understanding of the risk. In all of this, we cannot forget that the first and the most important things is to preserve the cultural heritage value of such assets. So how does the cultural heritage value thus come into play? Because typically when any of these three approaches are taken, the risk is measured in, let's say, monetary terms, i.e. what is the cost of the repair against the cost of the total loss of the building. But here is not the loss of the building, is not so much the loss associated with its, let's say, market value, but it is of the property, but it's the loss in cultural terms. So one way of defining that value is, for instance, to look at its significance. And to look at its significance means to, for instance, understanding whether it is of an asset of international renown. It might be considered a World Heritage. It might be characterized by particular elements that are of value worldwide. So this is the Cathedral of Manila, and for the ones of you that are familiar with the Cathedral of Lima, I'm sure that you will see many similarities, at least in the overall structures and in some of the decorations. Clearly losing even a little bit of an archway or a bit of the central vault here will be a disaster. So that is the approach. And indeed, both cathedrals are, I think, World Heritage assets. Or they can be of national significance, in which case we can consider that the value is slightly reduced, or they have local significance, or maybe modest significance only for the local community. That doesn't mean that the local community has less of stakeholders in such building, but when prioritizing, of course, we need to have a way of scaling this down. And then this can be further scaled depending on other elements that I'm not going to discuss here, but you can look at the project Cherish to get more information. What instead I want to talk about a bit, and this is something that was developed also by Dr. Putrino in a PhD dissertation, is a simplified analytical approach, which allow us to model the effect of all the hazards on these buildings, the three hazards that we have mentioned, earthquake, flooding, and wind, and that allow us to quantify their vulnerability and therefore to determine which hazard has the greatest effect on the same building, and secondly, how we are going to retrofit it. So we will concentrate specifically on the level of hazard that is causing collapse, and we will use very simple methods, which is typically taught in, let's say, the last year of undergraduate studies, or at the master level of undergraduate studies, and therefore engineers can use throughout the world. This is the yield line theory. Typically, yield line theory is developed for concrete structure, concrete slabs, but indeed can also be used for to work with masonry walls. And basically, it determines how the wall will fail and collapse by developing cracks when loaded out of plane. The behavior is quite complex because the wall will be subjected, as we can see here, to horizontal bending, to vertical bending, and in being subjected to horizontal and vertical bending, there will also be torsions. But if we can describe each of these effects at local level, we can then develop some relatively simple equation that can be used at the level of the panel in order to determine their capacity. And in order to further simplify things and make it scalable for different hazards, we have also simplified the loading. First of all, instead of considering the dynamic effect, we are considering the static effect. But also, instead of considering the impact of the load and its distribution on the whole panel, we are considering the resultant of this surface distribution into individual line loading, because this one makes the whole problem more simple from an analytical point of view, from a mathematical point of view. So we will see that we have then done various calibration to make sure that this actually doesn't defines the results, doesn't affect the results. So how do we approach this? For each type, in order to have a general method and generic methodology, we need to consider many different types of walls with different geometry, different aspect ratios, different type of constraints, different type of layout, presence or not of windows, and this will give us different type of groups of, let's say, walls panels. We then need to consider different size, different ratios, as I said. We need to consider the relationship of the size of the panel to the size of the units of the brick and walls. So we will also consider different size of the units and different material characteristics, i.e. their capacity to resist flexures in two directions and also the capacity of resist shear. We can then, once we have this wide range of possible, let's say, this generic sample, we can then define a set of increment of the earthquake or the hazard that we are considering in terms of their intensity. And then we can look at the proportion of each of these that fails for a given particular level of hazards. And by doing logarithmic regressions, we can then determine the cumulative fragility functions for each hazard and for each of these, let's say, wall types or panel types. And we will see that we can aggregate them in different ways. Before going a little bit, before going on to the results, and please let me know how much more time I have, if anything. We can look at what are the, let's say, the inputs, but also at the fact that, again, we need to consider how the cracks will form in the real brickwork. And this will be strongly influenced by the resultance of the load at a particular height. So for instance, if this is flood loading, we know that the flood will have a hydrostatic distribution that is triangular, and therefore the resultance will be at about 1/3 of the height if the flood goes to the full height of the wall. And that push at that level will create the failure. By using the virtual work and by considering the equation between the load applied and the internal resistance of the work done by the applied load and the internal resistance and dissipation of energy done by the moment, we can then equate and optimize, and we will find the minimal collapsal factor, which I will identify the intensity by which the wall is failing. So in order to generalize this for each of these cases, we have done 264 simulations for each boundary condition, changing the geometry and everything else, and the characteristic of the materials and the characteristic of the bricks and the presence of the opening and so on and so forth, so that we have a sufficient set to then do regressions. This is done via a very simple, or not so simple, but relatively simple, let's say, Excel-based and Visual Basic based technique program that basically consider a large number of possible paths to collapse and then converges on the one that provides the smallest collapsal factor, as I already mentioned. And the collapsal factor will be the one that gives the value of 1 for and identify that intensity measure. So we can then consider a large range of PGAs, water depths, or wind speeds, so accelerations, in order to get the regressions to determine the mean and the standard deviation of our regressions. And this brings us to considering a number of different fragility functions. So here, for instance, we are looking at fragility functions for different groups that represent different constraint conditions. Or if we, very often when you go on site, you will not know what the constraint conditions are initially. So you will only have the geometry. So we cannot discern between these different groups. So we have just one unique fragility functions that gives us the particular that gives us a particular fragility for the entire group. And this, as you can see, is different. Or if we have a lot of information, we know about the strains.
A su diablo.
Hello?
No sé, ¿qué voy a hacer?
There is some background noise. So we can then consider
Entonces, en este caso podemos considerar
shapes, and we can then
las diferentes
consider
formas,
the different constraint conditions and
las
the
diferentes
different and the
condiciones de
presence
restricción
and the presence, for
y
instance,
la
of
presencia de, por ejemplo,
or windows and so on.
de ventanas y la posibilidad de estas ventanas o no.
Now, I don't think I have much time, so I would like to give an example of how we have applied this to the Philippines. So here are some images of the heritage of houses and convents in the Philippines.
Con el patrimonio de casas y conventos en Filipinas.
And I have, and we have the range of possible values of the hazard for return periods, which are specific to the, let's say, to the event, but have the same level of alert for the Philippine national government. So these are buildings that are built in unreinforced masonry with some stone masonry with a particular way of also keying in the stones. Usually they are 1 or 2 story high, but the second story is made of timber, as we can see here. And we can then, there are complex facades. So depending on the presence of, for instance, internal walls here and the presence of the window, we can divide the complex facade in panels, and we can analyze the panels separately, associating them to a particular group, which is then modified with the opening. As you have seen, earlier, they were opening only in 2 types of groups, but now we are also considering the opening for other groups. So once we have, and this is of the, we have tried this on 29 facade, we obtain about more than 90 panels, and these panels can be categorized in as the pies that you see down here. So these are, for instance, 2 examples in where the upper and lower constraints will also be dependent on the type of flooring and the type of roof that we have, whether the roof is tied in or the floor is tied into the structures, which is something that is common, again, not only in the Philippines, in this type of constructions, but also in Peru. And depending on that, we will have different collapse mechanisms. So this is the range of, these are the parameters that we need to run our analysis. As you can see, there are only 12 parameters, and these are the range of values in the samples that we have identified. And these are some of the results. So what we see here, is that the Philippine fragility functions that we have derived for these parameters are in general weaker than some of the functions of the group that we have done in the general sampling on one end, but on the other end, we need to consider that there is a large proportion of these samples with opening, while these were without opening. The behavior is similar And we can then look at, for instance, what are the particular values for return period, for instance, of a PGA of 475 years, which is around 0.03. We can see here that the probability of being damaged is 40%, which is quite high. A typical flooding with 100 years return period is between 1 and 1.5 meters. Let's say 1.25 will give you a 50% probability of being damaged. And again, typhoons with a 25 meter per second will give you a probability of being damaged that is quite high, but this one concentrates specifically on very thin walls. So all this considered, we can then start thinking about what are the interventions that are most important and are most needed. On the other hand, it might be that we are not in a position to do any of this calculation because we don't have enough, we don't even can approach the 12 bits of information that I mentioned earlier. So, but how we can do an empirical approach. Here I have a very simple approach for the flood vulnerabilities, where, however, we are able to go all the way to the flood risk assessment. So, and we are concentrating on the south of the island, of the southwest of the island of Bohol. So we identify the area, we identify the parameters that are specific to each building. We then determine the data collections, and we create what we call a vulnerability index, which is the results of the scoring of each of the index. This provides us with a vulnerability curve for the samples. And we can then determine damage functions, which includes economic losses, but also historic values. And we can then, for each of the building and for each of the water depths that is associated to a particular position, identify the specific the number of buildings that will be in a certain value of that depth, and therefore the overall cumulative risk and cost to the of repair or mitigate. So this is, for instance, the case for again some of the churches in the southwest of Bohol, and you can see that the level of flooding or the level of a storm surge is different for the different churches, depending with an 100-year return period. These are the type of information that we collect, and this is in relation to the convent in Cebu. So we want to, and we can see here clearly what is the effect of this flooding on this building. So, and how this can be prevented, for instance, from having barriers or for having solution to the outside of the building, so that the water will not reach the structure itself. Such as, you know, the level of the drainage system, the surface permeability, the creation of a plinth. Very often these buildings don't have plinth, and the internal flooring is lower than the external level of the ground. So we can create a distributions, as I said, for each of these indicators, and for the scoring that we go through, that distribution can be divided in quartile to decide which are the ones at greatest risk. And then we can associate a level of risk at each of them. And if we repeat this process for all other hazards in a similar way, just by using a number of indicators and considering different effects, then we can actually arrive at qualitative risk assessment, which again allow us to compare the different risks associated to the different hazards, and therefore to make decisions in terms of the mitigation that needs to be taken. So this concludes my presentations. I'm sorry if I've gone a little bit over the time. The objective is to find the right balance between accuracy and simplicity, especially when we are dealing with so many different assets and heritage assets. The limitation is due to very often to the hazard characterization. So what do we know really about the hazards and how good it is, the availability of data, and that will determine the data collection strategy. Collecting data is always very expensive, so it's very important to know what data is already there. Whether the engineering expertise is there and it's available to identify the failures mode and to identify how to compute their capacity, and then the ability to determine commensurate fragility function for different hazards that can be then used to determine effective risk. And these actually they have a very good visual, let's say, character and content that can help effectively communicate a risk to the administration and help in the attempt to secure investment. With this, I think I will stop my share, and thank you again for listening.
Thank you very much, Professor D'Ayala. And now we give the floor to Professor Pere Roca for his contribution entitled The ICOMOS ISCARSA Guidelines on the Analysis, Conservation, and Structural Restoration of Architectural Heritage. Thank you very much, Professor Roca.
Thank you very much. First of all, I want to express my gratitude for this nice opportunity to present part of the work of the ICOMOS ISCARSA committee. I want to express my gratitude to Professor D'Ayala and also to the organizers of the webinar, because I think that certainly with this audience, we may enjoy a very nice opportunity to share part of our ideas, our work to interested engineers and architects. So I think that, well, what I will focus on are the new guidelines on the analysis, conservation, and structural restoration of architectural heritage, in which the ISCARSA committee is now working. ISCARSA stands for International Scientific Committee for Analysis and Restoration of Structures of Architectural Heritage. It is a committee of ICOMOS. I think that ICOMOS is well known. In any case, ICOMOS stands for International Council on Monuments and Sites, non-governmental organization dealing with the conservation of monuments and historical sites. ISCARSA is a forum and network for engineers and architects interested in restoration, in the care of building heritage. It includes more than 100 expert members and 40 associate members from many different countries. The main output of ISCARSA so far have been the principles for the analysis, conservation, and structural restoration of architectural heritage that were adopted by ICOMOS in October 2003. One of the reasons to work in these new guidelines on conservation of historical structures is in the scarcity of international documents specifically oriented to heritage structures. By that, I mean documents actually focusing on the structural dimension of historical buildings, the structural problems. Actually, I can only mention two documents. The first are the ICOMOS ISCARSA principles, which I have already referred to. The other is the Annex I on heritage structures of the ISO 13822 standard on assessment of existing structures. However, it turns out that the Annex I of this ISO standard is also largely based on the ISCARSA principles. So why working in a new set of ISCARSA guidelines? Which is our purpose with the new guidelines? Well, we want to assist in the application of the ICOMOS ISCARSA principles in real practice. The ISCARSA principles, I think, are a very helpful, very relevant document. However, the practical application of the principles may encounter significant difficulties in real practice. Second, we would like to address and provide clear ideas on some critical concepts related to the conservation of historical structures, such as the concept to which I will refer later of minimal intervention. Of course, working in the guidelines offers a new opportunity for discussion and elaboration. And of course, all of you are invited to participate, to place to me or to any other member of ISCARSA any possible comment, any possible question that may help us in improving our guidelines. And also, we would like to align the application of the principles of the ISCARSA principles with the ISO 13822 document, and especially with its Annex I. We need to converge to make the documents closer to each other, especially with regards to terminology, which shows some differences between the two documents. The new proposed contents for the guidelines is as follows. First, we discuss the general criteria on conservation. Then we discuss the three subsequent phases of the study of a historical structure, namely assessment, structural performance verification, and then intervention. During this discussion, I will refer to this and discuss these phases. Then there is also a section on quality assurance, and then another section on the explanatory report, which is a final report that should summarize the hypotheses adopted in the study, the methods, and the conclusions reached through all the activities carried out. I will, as I said, focus here on the general criteria and then on the phases of the study. As I said, the phases are diagnosis or assessment, structural verification, and intervention. So let me focus on them. But first, let me state with more clarity which is the purpose of the guidelines, which is our purpose in writing the guidelines. First, we want to provide criteria and assistance for the study and intervention on heritage structures. In particular, we would like to provide guidance in the application of more fundamental documents, such as the ISCARSA principles and the Annex I on heritage structures of ISO 13822 that I have already mentioned. The guidelines that we are now developing are based on the premise that the study and care of architectural heritage requires a combination of both scientific and cultural insight. The design of an intervention must be oriented to identify the best possible solution, considering both the structural performance, which requires us to think about the structural requirements, what the structure should be able to attain in terms of safety, of satisfactory performance, to avoid any problem to people. However, in this context, also the heritage values have to be considered. Along with the structural performance, we need to consider how possible interventions may influence, may impact on the heritage values in which the cultural value of the building is residing. The guidelines mention repeatedly the multidisciplinary team, the importance of the multidisciplinary team. We recognize that investigating a historical structure is a complex activity which requires the knowledge of many experts which should be involved. All this knowledge provided by different experts is indispensable for the success of the study and the design of a suitable intervention. Still speaking about the purpose and the multidisciplinary team, the guidelines are actually addressed to the entire multidisciplinary team. They are also expected to be useful to authorities and decision makers with responsibility in conservation of architectural heritage. And as a very important idea, a bit challenging, however, the guidelines are not only meant for very important individual monuments, they should be also applicable, we would like them to be also applicable to more modest works or buildings that may attain cultural significance because of their contribution to the identity of an urban or rural setting. Well, a very central idea in the guidelines is that selecting appropriate interventions should be based on the evaluation of their impact on the heritage values. The heritage values that define the cultural value of the building or monument, which means that, first of all, we should be able to identify the heritage values and the character-defining elements that contribute to these heritage values. Again, this is a task entitled to the entire multidisciplinary team. All the multidisciplinary team, including architects, archaeologists, engineers, historians, chemists, and other possible experts, should contribute to the task of identifying the heritage values and the character-defining elements. However, the guidelines try to help in this activity. They try to help in identifying some possible character-defining elements. We distinguish between tangible and intangible character-defining elements. For instance, among the tangible character-defining elements, we identify the geometry, including the shape, the spatial configuration, the formal design, the materials and fabrics, the overall structural organization, the construction details and the connections between or among elements, the location and setting, either urban or rural, significant historic modifications. We understand that all architectural additions that may have been produced in different historical periods contribute to the final configuration of the building and should be respected. And perhaps even more controversial, we also believe that imperfections and damage should be also identified as character-defining elements and should be respected because they also contribute to the final configuration, the historical configuration of the building. What the building finally is, all the aspects that may have influence on its history, its final configuration. However, imperfections and damage should be only respected, provided that they do not compromise the safety requirements of the structure durability. Among the intangible character-defining elements, we identify the construction traditions and the techniques, historical techniques, as revealed by the structure, the structural concepts and the resisting mechanisms of the structure, the original use and function, all the evidence on ancient knowledge, ancient practices, culture, cultural associations, technologies, as also revealed by the structure, and the spirit and feeling conveyed by the historical construction, among other possible intangible character-defining elements. We also suggest, as a very central idea in the guidelines, that any intervention on a heritage structure, we recognize that any intervention on a heritage structure will cause, to some degree, certain positive or negative impact on the heritage values. We should be able, at this stage, to identify the heritage values and should be also able to quantify the possible positive or negative impact of possible interventions on the heritage values. At this stage, we are in the condition of introducing the concept of minimum intervention. That's also a critical concept which recurrently appears in the guidelines. we propose a definition. Minimum intervention is defined as an intervention that optimally combines compliance with structural requirements with the maximum possible protection and enhancement of the heritage values. We should obviously comply with the structural requirements. I will insist later on this. However, we should do so in a way that allows us to respect and even enhance the heritage values identified in the building. Obviously, the minimum intervention must ensure the protection of human life while also paying attention to environmental issues and cost effectiveness. Actually, the guidelines are largely devoted to discuss on the strategies and approaches that may lead to the design of minimum interventions, and I will try to briefly refer to them and to illustrate how the guidelines actually intend or assume engineers and architects to deal with these difficult problems. The minimum intervention, therefore, should be oriented to preserve and even enhance the heritage values, and it should do so by means of optimal conservation operations of high technical quality. A very important idea, perhaps also controversial, but very important to us, is in the compatibility of structural performance and conservation. Other experts, in some occasions, have presented structural performance and conservation as contradictory requirements or aims. We believe that they are not contradictory aims, just the opposite. They can be seen as complementary conditions, not in contradiction, that may lead to convergent optimal interventions. We know because of experience, even regarding the intervention of buildings experience severe damage because of earthquake, we know because of experience that the minimum intervention approach is often also the most efficient and reliable from the point of view of the structural performance. For instance, after many real experiences, we have understood that strengthening solutions that do not radically alter the structural response are often those more efficient also from a resistant point of view. The guidelines recognize that conventional calculation techniques and legal codes or standards, which are normally oriented to the design of modern constructions, may be difficult to apply or even inapplicable to ancient constructions. Therefore, we need an alternative approach. Conventional calculation techniques and legal codes may not be useful for the study of a historical structure. We need an alternative approach. We, as an alternative, propose a more flexible, multidisciplinary approach, strongly based on the scientific method and based in the combination of at least 4 activities. The 4 activities are the historical research on the building, inspection, oriented to investigate the present condition of the building, decay and damage in the building, monitoring, and structural analysis. All the activities being equally important and having to be correctly integrated in the study. Those are complementary activities. I insist in that they are all very important, equally important, and also that they should be conveniently integrated, combined in the analysis. Let me speak about the 3 phases of the study. We distinguish among 3 phases: assessment, structural verification, and intervention. All the phases should follow consistently to each other. They should base mostly on similar and consistent approaches, criteria, and methods. The methods we use for assessment should be also applied to structural verification and even to intervention. The criteria and methods should be consistently used across the entire process leading to the final design of intervention. So let me now briefly discuss the 3 phases, starting by assessment. Assessment includes all the studies needed to obtain conclusions on the present condition of the building and the causes of existing decay and damage. It includes all the data acquisition campaigns and investigations needed for the study to reach the conclusions, such as laboratory testing, field testing, and others. It is directly based on the combination of the activities that I have already mentioned: historical and architectural research, inspection and investigations for architectural and structural documentation, monitoring, structural analysis, which is meant in the context of assessment. Structural analysis is meant to investigate the performance of the structure under a variety of past actions, and in this way contribute to diagnosis. By simulating past actions, we can try to understand how these past actions have contributed to the present damaged condition of the building, to understand what have been the actions that may have contributed to damage, and in this way to conclude on the condition of the building and the actions or causes that have contributed to its final damage condition. Let me now speak about structural performance verification, in which in the guidelines we may be suggesting some, I think, more controversial ideas. Let me first speak about the aim of structural verification, performance verification. Let me do so by showing this well-known fresco by Giotto in Cappella degli Scrovegni in Padova, in which we see the people that, of course, must be kept in good condition, in safe condition in the building, in the intervened building. But we also see the building itself as a cultural heritage object that must be preserved, taking into account its heritage values and character-defining elements. And then we see the fresco with its highly value. We have actually three elements: the people, the building, the fresco, or the very valuable immovable heritage attached to the building. So structural verification in the case of a heritage building involves obtaining conclusions on the structural performance and the possible need for a strengthening intervention. And this activity, the obtention of conclusions on the structural performance and the need for intervention, should take into account three intimately related but different targets, including people, the safety of people at risk, first. Second, the integrity of the structure itself as a cultural heritage object, taking into account its authenticity. And third, the safeguard of possible, valuable, immovable, cultural, and artistic contents. We have three elements, three targets that have to be simultaneously considered in considering the structure's performance and the possible need for strengthening interventions. Regarding the safeguard of valuable, immovable, cultural, and artistic contents that may be fixed to walls or walls in the building, we suggest the adoption of specific serviceability limit states oriented, obviously, to limit deformation and cracking that could damage these paintings or frescoes fixed to the structure. A potentially controversial idea, which I would like to offer to everybody regarding the guidelines, is the possibility that we consider about reconsidering the structural reliability levels. We mentioned that in some cases, protecting the structure's heritage values may require the acceptance of a safety reliability level lower than that implicit in building design codes. We, in other words, are available to lower the safety reliability levels considered in the study and intervention in the building. The need to do so to reconsider the reliability levels may appear when a satisfactory solution with sufficiently limited impact on the structure's heritage values is not possible. Finding a solution, an intervention solution with sufficiently limited impact on the heritage values may not be possible in cases with when the structure shows severe damage or very important, very severe structural deficiencies. We accept this possibility. We are available to reduce the safety level, the reliability level. However, we also state that in these cases, when we reduce the reliability levels, we should adopt parallel measures to limit the consequences of a failure on people. The consequences of a failure on people should be kept within reasonable limits, sufficiently limited risks. Therefore, we should be available to adopt possible measures to limit these risks, as for instance, a restricted use of the building or provision of alternate escape routes. Yes, we accept the possibility of reducing the reliability levels required to the structure. However, when we do so, we should in parallel adopt parallel measures, adopt complementary measures to limit the risk on people. As for assessment, we also have a proposed approach for structural verification based on the combination of 4 activities. The 4 activities, which are similar to those presented for assessment, in this case are historical analysis based on the investigation of the past performance of the structure. Second, qualitative, also called comparative analysis, which is based in the comparison of our building with similar constructions whose behavior is already understood. Then experimental analysis, consisting in the execution of on-site experiments aimed to measure the load capacity of structural members. And finally, but not less important, the analytical approach based on the use of structural analysis to predict the performance of the structure under future actions. As you will remember, I mentioned that in assessment, the structural analysis is oriented to analyze the performance of the structure under past actions. In the frame of structural verification, the structural analysis is oriented to predict the performance of the structure under future actions. We clearly state that this activity requires, for a calibrated and verified model, there is the need for model calibration and verification. And in the guidelines, we offer a discussion on methods, on approaches, possible approaches for model calibration. Let me now speak about intervention. First of all, regarding intervention, we mentioned some intervention criteria. Those criteria are aimed to facilitate identification of minimum interventions. I think that some of those criteria are well known and perhaps don't deserve much discussion here. The compatibility criterion, I think, is well known. The new techniques and materials should be compatible with the original techniques and materials. The durability criterion is also an obvious criterion. The non-invasiveness criterion, meaning that the new devices should not penetrate inside the original material, I think is also a well-known criterion. However, we include the formulated criterion, the criterion of removability. By it, we mean that whenever possible, the measures adopted should be removable so that it may be possible to replace a former intervention with a more suitable one. Then we also introduce the criterion of retreatability, according to which any intervention should not compromise future interventions. This is a very important criterion that should be always respected. As a general rule, any intervention should not compromise future interventions. This criterion is of utmost importance when the removability one cannot be applied, when a removable intervention is not possible. In that case, we should make sure that the intervention, the non-removable intervention, complies with the recruitability criterion. Other criteria that probably don't need much discussion are those of feasibility, controllability, and sustainability. Then we offer a discussion on how to apply these criteria in practice. We recognize that applying, enforcing all these criteria at once simultaneously may not be possible. We need to be flexible. We recognize that the criteria should not be regarded as absolute principles. However, they can be seen as guidelines or inspirational principles that may assist in the design of solutions approaching the concept of minimum intervention. And then we also propose a possible approach, an engineering approach for the design of the minimum intervention based on these criteria. The proposed approach is based on this flux diagram. I will quickly describe how it works. According to the approach, the engineering approach that we suggest to use, first of all, we need to set up some relativity levels. The reliability levels to be requested to the structure have to be, first of all, defined. After setting the reliability levels, we may start by envisaging the process by envisaging possible intervention solutions. A number of alternative solutions should be envisaged. Solution 1, solution 2, solution N. As many as possible alternative solutions should be envisaged, all of them satisfying the requested reliability levels. Then for each of the solutions, we should measure the impact on the heritage values. And therefore, we have an impact 1 for solution 1, impact 2 for solution 2, impact N for solution N. We should then compare all these impacts and retain the solution with minimum impact. The solution with minimum impact should be then selected with minimum impact on the heritage values. Remember that all the solutions, including the one with minimum impact, all of them satisfy the requested reliability levels. Then we should investigate if the impact of solution I selected as the minimum impact, as the one with minimum impact, if this impact of solution I is sufficiently small. In other words, whether the benefit of the solution is much larger than in costs in terms of loss of cultural value or impact on the heritage values. The benefit is the enlargement of the lifespan of the structure, the increase of the safety of people, the safety that people may enjoy in the building, and so on. The cost is the reduction of the cultural value, the impact on the heritage values. We should make sure that the benefit is much larger than the cost, meaning that the impact is sufficiently small. If the impact is sufficiently small from this point of view, the solution selected can be considered to be a final minimum intervention, and we can retain and present it as the minimum intervention, as a targeted minimum intervention. Otherwise, we may need to reconsider the structural requirements. Remember that when reconsidering the structural requirements and reducing them, we then need to adopt complementary measures. And by adopting a reduced reliability levels, set of reliability levels, we then can start the process, envisaging new solutions, and try to finally reach a satisfactory minimum intervention with a sufficiently small impact on the heritage values. This means that we should be able to quantify the impact of interventions on the heritage values. This may be a difficult task. However, the approach proposed actually requires to investigate the impact of interventions on the heritage values. We can do so at least in a qualitatively way. At least we may try to qualitatively categorize the impact of interventions. In the guidelines, we try to help in this task by distinguishing among three categories. The first category involving solutions with positive or low negative impact. A second category with moderate negative impact. Another category with high impact on the heritage values. There is no time to discuss all these categories. Let me, however, present the case of interventions with positive impact or very reduced, very low negative impact on the heritage values. In this category, we consider maintenance solutions, stabilization operations, repair interventions or strengthening interventions. First, preventive or regular maintenance operations that do not produce any sensible alteration on the existing material. Second, stabilization operations with fully non-invasive and removable technologies carried out with fully non-invasive and removable technologies. Third, repair interventions carried out by means of appropriate techniques. By that, we mean that they are based on proven, compatible, and durable materials. And finally, strengthening interventions which satisfy two complementary requirements. They should be based on non-invasive and removable techniques, first. And second, they should be preferably based on traditional or historical techniques with proven compatibility and efficiency. With that, I finish with some final remarks. As you have seen, we propose to carry out the study basing on a multidisciplinary, flexible, and broad approach, which is based on the combination of different activities, including historical research, inspection, monitoring, and structural analysis. The minimum intervention is presented as the main target of the entire envisaged process. However, finding a minimum intervention requires first to identify and investigate the heritage values, and then to evaluate the impact of interventions, of proposed interventions on the heritage values as part of the decision-taking process. We also propose an engineering approach for the identification of minimum interventions that, as explained, is based on the investigation of a set of possible alternative solutions. With that, I finish. Thank you indeed very much for your attention.
Thank you very much, Professor Pere. Very, very interesting presentation. And now we leave the floor to Dr. Victor Carlotto for his contribution on conservation experiences in the three pre-Hispanic sites in Peru, Machu Picchu, Coquequirao, and Karaal. Dr. Carlotto, the floor is yours.
Hola. It's okay. Good morning. I just want to thank all the organizers of this event. I am going to present the geology and conservation of Machu Picchu and Choquequirao first, and the end of Karaal. This presentation is based mainly on work done many years ago, as you can see in these 3 bulletins, but the result of these investigations remain in implementation, particularly in Machu Picchu. Machu Picchu and Choquequirao are located in the Eastern Cordillera of southern Peru, which is traversed from east to west by the Vilcanota and Apurimac rivers, developing abrupt canyons. These 2 sites are separated by mountains that exceed 5,000 meters, and which were very important in the religiosity and cosmovision of the Incas. In Choquequirao and its surrounding, including the access road from Cachora, schist, mica schist, gneisses, and quartzite crop out, while most of the sanctuary of Machu Picchu is found in the Machu Picchu batholith in red, where the granite predominates. The Inca city of Machu Picchu is built on intrusive igneous rock, which are cut by faults and fractures that have controlled the geomorphological evolution. Recent deposit and quaternary soils contain granite blocks that have broken away from the main rock body, forming what is known as granitic chaos. Additionally, ancient landslides such as Cerro Machu Picchu and recent superficial landslides have been identified. In order to begin with the topic of conservation, it is important to remember that between 2000 and 2001, the Japanese mission led by Professor Sasa gave a hypothesis indicating the existence of a large deep landslide that would destroy Machu Picchu. These ideas attracted international attention, and the international consortium was set to evaluate this hypothesis. The Japanese, Italian, Czech, and Peruvian Canadian mission conducted geophysical studies, satellite and terrestrial interference, extensometer and dilatometer measurements, etc. The conclusion in the 2005 international workshop was that there is no large deep landslide that may affect or destroy Machu Picchu. Here, the signed document. I will share some examples of the studies. The Geological Service of Peru, INGEMED, carried out the geomechanical study and evaluation of the stability conditions of the proposed landslide. The stability analysis, which include calculation parameters such as cohesion, friction angle, seismicity, and presence of water in the failure, has shown that the Inca city of Machu Picchu is stable under extreme conditions. This is the graphic. All the condition of the calculation parameters indicate that the Machu Picchu is stable. In addition, the geophysical studies carried out by the Peruvian Canadian mission do not show deep landslide as indicated by the Japanese, only superficial slides which were stabilized by the Incas, as we see here. The georadar in the sliding fault zone does not show any evidence of failure, but substrate and filling which the Incas made to stabilize the granitic chaos. To explain the phenomena that affect Machu Picchu, we first need to explain the geomorphological conditions which the Incas found before building the city, that is, the presence of what is called granitic chaos or granitic block accumulation. The origin of granitic chaos is evidenced in this picture. The granite cut by fracture and faults are affected by water and will produce blocks separated by gravity. The Incas built a series of terraces, platforms, and containment walls to stabilize the granitic chaos. It was only after that they started building houses, temples, and palaces. A quarry of this rock is still visible on one side of the city, and it explains how this granite chaos was in the process of being stabilized, but it was never finished. During the Inca occupation, the terraces, platforms, and buildings were adequately preserved by gutters and roofing, which helped to evacuate the abundant rainwater, but this is no longer intact. The drainage system had not been maintained, which allows the water to penetrate the soils. This water washes away the clays and silts that act as a matrix between the blocks of granitic chaos, and also lowers the resistance to soil's movement. This, in turn, causes the rocks to sink, as is evident in the Temple of the Three Windows, the Temple of the Sun, and the other constructions. This settlement caused imbalance and separation of the joints, the areas between stone and built stone, as can be seen in the window of the Sierpes in the royal tomb or in the room of the Nustas. These movements occur very slowly, but if this trend continues, the construction as the main temple will be seriously affected in 20 to 30 years or maybe collapsed. The city area has also experienced numerous superficial landslides, although many of the most susceptible areas were stabilized by the Inca terraces. However, here too, the lack of adequate and operative drainage system has caused the reactivation of landslides, as can be seen in the western and eastern slope of the city. As a background, starting in 80s, the detailed geological and geodynamic mapping of Machu Picchu was carried out. In addition to the rocks and faults, the surface landslides, settlement areas, surface erosion, etc., were mapped, as well as the infiltration zones, preserved and destroyed Inca drains, all this in order to give the recommendation that might serve to the conservation and maintenance plan of the Inca city. Basically, two subjects are considered. First, the construction of waterproof floors to replace the lack of roofs, and second, restoring the Inca drains. This prevents rainwater from causing settlements, landslides, etc. In effect, these recommendations have been implemented since that date and began with the Temple of the Sun, and it is currently continuing to advance a large part of the city. In this map and photos, we can see the waterproof floors or impermeable surface in the direction of the drainage system already restored, which has stabilized the settlements in this area of the Temple of the Sun, including these passageways. This is the same passageways. These photos and map correspond to eastern part of Machu Picchu, where the waterproofing of floors and restoration of drains is recent, of 2018 and 2020, and it's based on previously carried out studies. Therefore, this process has been implemented throughout the Inca city. As conclusion and recommendation for Machu Picchu, we can say the phenomena that affect the Inca city are superficial and whose origin is directly related to the presence of water due to the lack of roofs and the non-functioning of the Inca drainage system. The recommendation is to complete the restoration of the Inca drainage system and the construction of the waterproof floors, which will allow an adequate evacuation of rainwater, which will avoid external geodynamic problems. Now, I am going to present Choquequirao. As we saw previously, in Choquequirao and its surroundings, schist, gneisses, and quartzites crop out, all affected by geological faults. These rocks were used to build the archaeological site. The most important quaternary deposits are of colluvial origin and generally originated from landslide. Choquequirao has been built in a zone of unstable landslides. The question is why the Incas choose this site. The answer we will see later. In this photo, we can see that Choquequirao was organized in two parts: high sector, or Hanan in Quechua, and low sector, or Urin, along a hill in a north-south direction, very similar to Machu Picchu. Here, we can visualize this large platform or andenes called Chacrandén. Here we can see the Hanan or upper sector with the Hanan temple, the Colca system or food warehouse, as well as channels and retaining walls. Here, the lower sector or Urin that hosts the most notable buildings of Choquequirao. Such constructions are arranged around the main square of Aucaipata that is surrounded by Ahuay Callanca, the main temple, and the andenes of the lower part or Chacrandén. In Choquequirao, there are landslides developed on the eastern and western slopes, leaving a ridge oriented north-south on a saddle between them. Close to this extremely unstable ridge, the Incas built Choquequirao, but previously they stabilized them due to the importance of the site. The most important part of the stabilization corresponds to this set of platforms called Chacrandén that has a length of 207 meters that managed to stabilize the major landslide. This colossal structure was built with large parallelepiped metric blocks of gneisses and schist. These platforms are separated by wide trenches of 4 by 2 meters that, in addition to the drainage, give greater support to the structures. According to the dimension of the walls, the foundation must be deep and may be lower than the major sliding plan, which will explain its stabilization. After the stabilization, the Incas built their colcas, temples, callancas, enclosures, fountains, and houses. All this stabilization system works very well after 500 years. The conservation problems are minor and correspond mainly to settlements, creep or slow landslides, surface erosion, superficial landslides. For example, this map shows the separation of joints in blue line and slight inclination due to differential settlement around the main square. Finally, in the Choquequirao area, there are platforms known as llamas that stabilize the western part and mainly the D8 landslide, which is in a very high slope area between 60 to 70 degrees of inclination. In the D8 landslide, the Incas built a system of platforms that are being restored, but the most important is the Andenes de las Llamas, which are located on the southern edge of the landslide and are partly anchored on rock. This platform system, in addition to having stair and step in the retaining walls, also have drainage system that allow the water to be efficiently evacuated. This Inca infrastructure has allowed the terraces to be preserved for more than 500 years, thus demonstrating their high knowledge in geological, hydraulic, and construction engineering. Here, a view of the platform of the Las Llamas, made of white quartzite rocks and the walls of dark schist. The mosaic constitute a large wall panel, which archaeologists refer to fertility, the movement of the sun, and the appearance of the certain constellation at certain times of the year. In addition, the interpretation indicates that the Choquequirao and Machu Picchu have many archaeological similarities, such as having been organized in two halves, Hanan High and Urin Low. The location of the site seems to have been careful, chosen and planned, based on relief, the Apurímac and Vilcanota rivers, the mountains and the glacier that surrounding the sites, suggesting a close relationship with water and fertility. On the other hand, the relief on the saddle back of Choquequirao is similar to that at Machu Picchu, a product of landslides. The great coincidence is the almost north-south direction of these reliefs. We think that the choice of these sites had to do with this north-south axis. Therefore, all engineering works had a very important goal: to make these sites stable, because among other things, they were elected to have favorable orientation for astronomical measurements and be able to follow the movement of the sun in east-west direction, and knowing the solstices and equinoxes, that is, organizing the agricultural calendar within a ritual context, one on the northern slope of the Apurímac River and the other on the southern slope of the Vilcanota River. Now, let's see Karaal. The sacred city of Karaal is the most ancient urban settlement with monumental architecture in America. Its antiquity has been confirmed by dozens of carbon-14 dates between 5,000 and 4,000 years before the present, and that it would have had between 500 and 600 years of occupation. It is located on the left bank of the Super River at an altitude of 300 meters in the central coast of Peru. The sacred city is located on a river terrace of the Super River and on alluvial deposit of debris flow at the mouth of the Chupasigarros stream. There is an overlap of alluvial deposit on the fluvial terrace. In this image, a transverse wind dune to the Chupasigarro Creek stand out. It gives the impression of being a containment dam. This is a geological map of Karaal where the most important quaternary deposits are shown. These are the river terraces of Super River and alluvial deposit of the Chupasigarro Creek. In the surroundings of Karaal, intrusive rock outcrop, such as the diorite in red, that were used in the construction. 4 alluvial events, A3, A2, A1, and A0 have been recognized and studied. The alluvium A3 and A2 are all pre-5,000 years, and the alluvium A1 and A0 are related to the history of Karaal. South of the dune, lacustrine clays have been found. It looks as if the dune acted as a barrier, forming a small lake. In this photo, we can see the alluvial and fluvial deposit, as well as Karaal Alto and Karaal Bajo, separated by the alluvial channel. In this map, we have marked the alluvium A1 that appears as the remain of a small channel C1 developed on the fluvial terrace. We think that it has been originated by the overflow of an alluvium A1, but that to a large extent it is covered by the alluvium A0 that is later. This alluvium A1 seems to affect the construction of Karaal Alto, particularly the circular structure, the central pyramid, and the pyramid of the Curry. By this relationship, we can say that the alluvium A1 would have occurred between 4,600 and 4,400 years before present, which is more or less the date of the construction of Karaal Alto. Here, we see the alluvium deposit A0 that affect Karaal. Interpretation indicate that this alluvium affected the dune and the northern part of the pyramid of the amphitheater. Then this pyramid was rebuilt and adapted to the new channel. Consequently, the age of this event A0 is during the construction of Karaal Bajo, that according to archaeologists is slightly posterior than Karaal Alto, and we think can be between 4,300 and 4,200 years. The dune is the southern limit of the sacred city of Karaal. It has a length of 600 meters, a width of only 10 to 20 meters, and pyramidal in shape. It covers the entire width of the Chupasigarro stream. Lacustrine deposits have been discovered to the south of the dune, but not to the north. This indicates that the dune would have acted as a bar, blocking rainwater, forming the small lake. It is interpreted that the dam was built by the people of Karaal after the A1 alluvium that affected Karaal, with the idea of protecting the city, but it acted as a small dam forming the lagoon. To know if there is dam under the dune, we apply the georadar penetration geophysical method throughout the length and width of the dune, and the result of which show that there are anomalies that appears to be block of stones. In conclusion, the geophysics indicates the presence of anomalies under the dune, which could be a stone wall. This wall could have been built by the people of Karaal between 4,500 and 4,300 before present, in order to stem an alluvium and avoid the destruction of the city. However, this artificial barrier or dam held to water back, forming a small lake, but was later covered by the dune. Within this graph, I want to show the chronology and interpretation of Karaal. Alluvium 2 is older than 5,000 years before present. Alluvium A1 affected the first construction of Karaal Alto between 4,600, 4,400 years before present. The dam would have been built around 4,500, 4,300 years before present to protect the city. The dam blocked the waters of Chupacigaro stream, probably related to the Niño phenomenon, and formed a lagoon. In full occupation of Karaal, between 4,300 and 4,200 years before present, there was a new alluvium A0 that destroyed part of the dune and the pyramid of the amphitheater. Finally, I want to say that the people of Karaal made highly engineered pyramidal construction that allow their conservation to this day after more than 5,000 years. That is older than the pyramid of Egypt. What we see here is the birth of Inca engineering. What is shown in the last slide, Machu Picchu. Thank you.
Thank you very much, Dr. Carlotto, for your very interesting presentation. We have some questions on the chat. So to Professor Dayala, to which authority level are the engineering recommendations on conservation and reinforcement measures, national, provincial, or communities? Who is in charge to implement them?
Thank you very much for this question. I think you referred to the specific case of the Philippines. In that case, there is a national commission for art and culture, which after the earthquake was helped by a national committee of monuments and sites, which asked us to help derive these guidelines for conservation after the two destructive events. The buildings that were restored by the National Committee and the buildings that were restored by the National Commissions were different and were approached slightly differently in terms of the type of restorations and the let's say, the level of extent of reconstructions and so on. In the one restored by the National Committee of Monuments and Sites, they try to follow a little bit more the Iscarsa approach that you have seen. The other one was a bit less. But it's quite interesting because the funding to actually carry out those restorations very largely relied on the local community and the local congregation to those churches. And they also depended very much on the entrepreneurship of the local clergy. And in the Philippines, the bishop and all the clergy are very motivated in the and let's say steeped in the knowledge of the restoration, the preservation, and so on, so much that every year they have a conference just on this subject. And all the priests comes together to say what they have done in their church in order to preserve them for the future. And they regularly invite international speakers from Iscarsa and from other, from ICOMOS and so on to discuss those themes.
Thank you very much. And to Professor Pere, the guidelines seem focused on the prevention of damage to buildings, but these are also applicable for rehabilitation or reconstruction after a damaging event has impacted the building.
Yes, thank you very much for the question. Is a good question. The guidelines are intended to be applicable also for intervention after possible natural disasters or man-made disasters also. However, we have a specific proposal. We call it the reparability or pro and post-natural hazards structural maintainability, according to which, rather than waiting to the hazard to occur and then reconstructing or carrying out a very substantial intervention, we think it is better to first foresee the possibility of the hazard, especially in the case of earthquake, but also other hazards, and already carry out maintenance, repair interventions, strengthening interventions of limited scope before the actuation of the hazard to improve the performance of the structure. After the action of the hazard, after a possible earthquake causing damage and maybe partial destruction, we also obviously accept the possibility of intervening. However, again, we believe that it is better to carry out limited interventions even after the hazard, oriented to recover the original performance of the building, or perhaps to improve it to a reasonable limit. In this way, to try to apply the principle of the minimum intervention also to these situations. By applying limited interventions, we think that we may try to preserve the best aspects of the performance of the building, to improve the building in the needed extent, and in this way to avoid very large, very impacting interventions, which, in addition of reducing substantially the cultural value and highly impacting on the heritage values, may introduce significant uncertainty on the real behavior of the building. We believe, after our discussions in the frame of the committee, we understood that very impacting interventions which introduce a significant alteration of the structure may have consequences on the structural behavior that may be difficult to predict and may be even counterproductive regarding the resistance or the performance in the event of natural hazards. I don't know if this answers to the question. I hope so.
Thank you very much, Professor Pere. To Professor Dina, we have another question. So the infrastructure has survived many years and in some way is resilient to period of return of the hazards. Has climate change accelerated or made higher the exposure of all our historical infrastructures?
This is a very good question. There is certainly an issue especially in relation to flooding. When we look at past hazards in many local basins, we see that, for instance, the return period for a flood of 1 meter or 1.20 meters might be 100 or 150 years. But when we speak to the local, the account is that now floods that are around 800 millimeters or are almost yearly occurrence. So this might be flash flood, might not be long-lasting flood, but they can sometimes be just as destructive, in fact, if not more. So there is certainly an issue of what we call the dynamics of exposures, and historical infrastructures that have survived today, and we can consider that, you know, we can have a relaxed approach, might not survive other hundreds or 200 years if they, for instance, you know, flooding or storm surge or intense rain keep falling. For instance, when I first went to the Philippines, I was astonished by the fact that a building that had lost their roof and had been damaged and abandoned, they were completely covered in vegetation after just 1 year of, but when I say covered in vegetation, it really means covered in vegetation. You could not see the walls. You know, this for people coming from Europe, this is incredible. They were saying that this was almost normal, but you can imagine the level of disruption and the level of damage that can bring to a building that has been already damaged by a natural hazard if it's not quickly intervened upon. And the repetition of the hazard is certainly something that create a weakening of the structures, and they might not be level events that create extensive damage in their own right, but if they weaken the material, so for instance, in the Philippines, the walls are made of coral stone, which is a stone very rich in lime, which it's very easily soluble in water, so they can, that deterioration then, if it's repeated every year, when an earthquake comes, then can have a very important destructive effect. So yes, the answer is yes, in short. I think there was a question, very interesting comment more than a question about the
recommendations that every community should be specialist in restoration, even
yes.
at artisan level.
Yes, and they should be trained. Yes.
Yeah. I have a personal question, which is more a curiosity for Dr. Carlotto. Obviously comes from a non-expert, and it's about granitic chaos that you mentioned. Is there any other natural aspect which can generate granitic chaos? You mentioned the presence of water, but is there any other reason for this formation, like ground movement or earthquake shaking, for example?
Normally, this chaos granitic is related with the rock and the structure of the rock, the faults, the fracture, all this normally is formed related to relief, no? The relief, the water and gravity.
Okay.
It is possible to relate it as seismicity phenomena, but in Machu Picchu, the seismicity is low. It's very low, because the batholith. Near the Cusco exist the active faults that produce superficial seism, but this seism not affect Machu Picchu. In this case, I think the granitic chaos is related to gravity, water, relief. That is.
Thanks a lot. Thanks for answering the questions to all from all speakers. So I think, let me just check the chat. I think we've answered all the questions in the chat box. So I'd like to thank very much all our speakers for their very highly valuable contributions. In terms of concluding remarks, well, thanks to Professor Dayala's contribution, we've clearly understood how to deal with the very important aspects of determining the physical vulnerability of heritage assets undergoing multiple sources of natural hazards, which is increasingly concerning aspects of today's society subjected to climate change, as we've pointed out. And the various methods developed to date to deal with the structural problems considered, by also including the very key aspect to consider in this case of cultural heritage properties, which is the heritage value. Thanks to Professor Roca, we've discussed some critical concepts related to the preservation of heritage structures, which relate to the definition of guidelines to rule the interventions allowed and the rules to consider when approaching these important aspects. Critical concepts such as the minimal interventions, where minimal intervention were investigated, as well as clearing the question, why do we need firm guidelines to approach those buildings, and the important role that they have in the protection of cultural heritage assets to be maintained, preserved, and safely transferred to posterity. Thanks to Dr. Carlotto, we have seen the very interesting aspects related to the geological and geomorphological aspects which hinder the three specific sites of Machu Picchu, Coque, Kirao, and Karaal, and how to assess this more effectively. So I'd like to thank you all for your contributions, very, very valuable. And also I'd like to thank Professor Jose and Lisette for the support that they've given us and they've given me personally in organizing this webinar, and to you all for having participated and having made this possible. I think I can conclude this webinar by wishing you all a nice rest of the day, afternoon, or evening, depending where you are at the moment. Thanks a lot.
Thank you very much to all speakers. Bye-bye.
Thank you.
And to the audience.
Thank you.
Thank you.
And thank you for the organizing.
Doctor José Macharé, como cierre, por favor, de este webinar, ¿podría dirigir unas palabras finales, por favor? Muchas gracias.
Thanks.
Yes, thank you very much. On behalf of Engineer Carlos Herrera, that has some health problems and cannot speak to you now, I just want to finish by thanking to our guest speakers that has been given such a high level to this seminar, to Dr. Putrino and Dr. Ayala, especially because for the coordinate of the organization, and some of our invitees and guests in the floor, Dr. Marcial Rivera, member of the CDRM from Costa Rica, that is always with us, Engineer Billy Zavala, and the INGEMET team on natural cultural heritage. Thank you to all of you, and the technical staff of the Colegio de Ingenieros, Karin, and also Lisette for their help, and all the participants, and we hope to see you in the next activity. Thank you very much.
Thank you.
Only ask to our speakers and people to open your the cameras for a final photograph, please.
Excelente, muchas gracias, doctor Macharé. Justo se me adelantó con el aviso. A ver, por favor, una sonrisa y muchas gracias. Ahí está. Excelente. Muchas gracias. Muchas gracias, doctor José Macharé, a nuestros invitados, expositores del día de hoy. Les agradecemos por estar presente, al igual a nuestros espectadores. Este evento está siendo grabado y va a ser publicado en nuestra página web. Igualmente lo van a poder ver a través de nuestro Facebook, porque igual se queda grabado para que puedan volver a apreciarlo. Igualmente van a poder contar con las presentaciones de nuestros expositores, que también van a estar colgados en nuestra página web. Cualquier consulta con respecto a los certificados pueden dirigirse al correo del procedimiento para que podamos atenderlos adecuadamente. Muchas gracias a todos ustedes y muy buenas tardes.
Bye bye.
Bye. Bye.
Bye.
Thank you. Up to the
Bye
next
bye.
time.
Thank you. Nice to see you all. Bye bye.
Bye bye.